Hello, my name is Itai Zumbunu from FutureSense, an EPM solutions company. Today, we're going to talk through some techniques for optimizing your planning and Essbase environments. The majority of concepts in this presentation will apply to both on-premise as well as cloud environments, with a few minor exceptions. So, what is optimization? Optimization refers to the techniques in which database performance or user interaction with that database can be improved. There are key items that can be looked at prior, in the course of, and post-project implementation. Let's get right into it. 10 steps to optimization. There are lots of things that can be done to improve a database. In this presentation, we will focus on 10 major items. Number 1, the reporting model. Of course, the business requirements are the key driver to the number of dimensions a model will have. But it is a rule of thumb. Minimize the number of dimensions. Try not to have everything in one model. The greater the number of dimensions, the more likely it is that you will run into database performance issues and vice versa. Minimize the complexity of individual dimensions. Consider using UDAs and attribute dimensions in order to reduce the size of some of the dimensions. This also has the added effect of reducing the size of the database, thus improving performance. Examine the level of granularity in the dimensions. Planning and Essbase databases are not usually meant for transactional level data. Therefore, keep the level of detail to a level that's absolutely necessary for planning and reporting purposes. 2. Outline order. Simply by counting the number of stored members in each dimension, you can improve database performance by ordering dimensions as follows: from the largest dense dimensions to the smallest dense dimensions, from the smallest aggregating sparse dimensions to the largest aggregating sparse dimensions to the non-aggregating sparse dimensions. This order is also referred to as hourglass on a stick. Why is this outline important? This dimension order relates directly to how the calculator cache functions. It determines how data is stored. It determines the size of the blocks. It determines some of the calculations for the database. It also determines the calculation order for dimensions. And it also determines how users can perform analysis. Thing to also keep in mind is that the effect of sparse dimension ordering is much greater than that of dense dimension ordering. 3. Dense sparse settings. Finding the optimal configuration for the dense sparse settings is the most important step in tuning a database. It directly influences your block size and number of blocks. You have to optimize the block size. Optimal block size, on the other hand, varies per operating system. But in choosing the best dense sparse configuration, keep in mind that large blocks tend to yield poorer performance. In general, the system runs optimally with smaller block sizes. Let's discuss blocks in planning and Essbase. Dimensions tagged as dense will make up the cells within a block. Dimensions tagged as sparse will create the blocks themselves. The system creates a data block for each unique combination of sparse dimension members that contains data. Tagging dimensions as dense and sparse determines the overall size and structure of the database. How do you calculate block size? Data block size is determined by the amount of data in a particular combination of dense dimensions. Data block size is 8 times n bytes, where n is the number of cells that exists for that combination of dense dimensions. As an example, if the accounts dimension has 1,000 stored members and the time dimension has 12 stored members, then the total cells in a block is 1,000 times 12, which makes 12,000. The block size itself is then 12,000 times 8, which makes 96,000 bytes. How do you reduce block size? A. You can change a dense dimension to a sparse dimension. You can make members in a dense dimension dynamic. You can apply the label-only member property where parent members do not necessarily have to reflect or store values. You can even also apply dynamic calc property to sparse dimensions so values can be calculated on the fly rather than stored. It's important to talk about block density. Block density is an indicator of the average percentage of data contained within each block. It is in the nature of data to generally be sparse. That's why even a block density of 0.18% can be seen on a database that runs normally. But in general, you want the density of your block to be as high as possible. You can manipulate and optimize your block density in conjunction with your block size by changing dense and sparse settings. A large block with high density is acceptable, but a large block with very low density would not be recommended. System tuning. System tuning is dependent on the type of hardware and operating system. The greater the spec, the better the performance. The more limited the hardware and operating system, the more likely you are to run into performance issues. Keep memory size higher wherever possible. Ensure there is no conflict for resources with other applications. Number 5, cache settings. The index cache stores data related to index entries, such as the location of data on disk. The data cache stores the actual data, often in a high-speed memory location. The data file cache stores compressed data files, often in high-speed memory location. The actual cache settings applied are dependent on your specific situation. To measure the effectiveness of the cache settings, keep track of the time taken to do a calculation and examine the hit ratio statistics in your database information. When on premise, don't leave a cube with the default cache settings. The rule of thumb here is to see if you can get the entire index file into the cache and make the data cache 3 times the index cache. On the database statistics, check to see the hit ratio on index and data cache. This gives an indication of what percentage of time the data being searched is found in memory. For the index cache, this should be as close to 1 as possible. And for the data cache, just as high as possible. This means that the index file, i.e., the pointer to the block, is always found in memory every time a search is made. The data block itself does not necessarily have to be found in memory. 6. Data loads. Knowing your database configuration settings, i.e., which dimensions are dense and which dimensions are sparse, allows you to optimize your data loads. Organize the data file so that it is sorted, starting with the largest sparse, and so on. In other words, in reverse order of the previously mentioned hourglass order. The most effective data load is one which makes the fewest passes on the database. Hence, by sorting on sparse dimensions, you are loading a block fully before moving on to the next one. Load data locally on the server. If you are loading from a raw data file dump, make sure the data file is on the server. If it is on a client, you actually might bottleneck on the network. 7. Optimize retrievals. You can increase the retrieval buffer size. This helps if retrievals are affected due to dynamic calculations and attribute dimensions. You can also increase the retrieval sort buffer size if you are performing queries involving sorting and ranking. Smaller block sizes tend to give better retrieval performance. Logically, this makes sense because it usually implies less input-output. Smaller reports retrieve faster. If you have a lot of dynamic calculations or attribute dimensions, these require calculations to be done on the fly as the data is not stored. This may also slow down retrieval performance. Higher index cache settings may help performance since blocks are found quicker. Optimize calculations. Unary calculations refer to the use of the outline structure to produce parent-child relationship calculations. Unary calculations are the fastest. Try to put everything in the outline and perform a calc-or when possible. You should fix on sparse dimensions and use if on dense dimensions. Fixed statements on sparse dimensions only bring into memory blocks with those sparse combinations which the calc has focused on. If statements on dense dimensions operate on blocks as they are brought into memory. Where certain members need to be calculated twice, use the 2-pass calc tag and try to avoid multiple passes on the database. The Essbase engine calculates blocks marked as dirty. Dirty blocks include updated blocks and their dependent parents. Use intelligent calculation in the case of simple calc scripts. You do this via the command set update calc on. Thus, the system will only focus calculations on updated blocks, reducing the amount of time it takes to complete a calculation. 9. Defragmentation. In planning and Essbase, fragmentation refers to unused space within a database. This can lead to increased data file sizes and potentially slower performance. The impact on performance is less significant with modern hardware and Essbase enhancements. Fragmentation occurs over time as data blocks are updated. As the data blocks are updated, they grow, and the updated blocks are appended to the page file. This tends to leave small free spaces in the page file, which in fact blow up the size of the database. The longer you run your database without clearing and reloading, the more likely it is that it has become fragmented. Incremental loads also usually lead to lots of updates on blocks, causing fragmentation. Many calculations, many passes on the database also cause fragmentation. The solution to fragmentation is defragmentation. You can perform an outline restructure using the alter database force restructure command. Alternatively, you can export data, clear all data, and then re-import data. 10. Partitioning and data maps. Partitioning allows for transfer of data from one Essbase cube to another. The phenomenon is pretty similar to data maps on cloud environments, where data is pushed from one application to another. By breaking up one large database into smaller pieces, calculation performance may be optimized. But because this adds a significant layer of complexity to administration, this is the last step in optimization that we have listed. It, however, does not mean that it has the least impact. In conclusion, it's important to distinguish between theory and practice. These are theoretical concepts towards optimization. What works in one environment may not necessarily work in another. It's important to know and understand the theoretical concepts behind optimization, but equally important to put that to practice by testing the changes. For more information, please visit www.futuresense.za.com.